Molecular bonds and bonding energy is based on the mass of, or energy of what makes it up and the orbital bond they form. This is why it takes energy to break bonds, and energy is released when they are formed, typically. If the two atoms that come into contact have enough energy to be free, but do not have enough energy to escape each other once they meet, they will release any excess energy they contain as the bond or orbital equilibrium is formed. So what I'm saying with this is basically I'm relating atomic bonds and bond formation of molecules to gravity. And so what's going on with these molecules is that they're bonded in this orbital motion, right? And so you can say that when two stars, get pulled in towards each other, they get locked into a sort of bond, right? There's this attraction between them where they can't really escape each other now, right? And they're now locked into this pair, this bonded pair. And so they continue to orbit each other, but neither of them have enough energy to escape, right? And so say that one had a lot of energy, right? But, when it gets pulled into this pair, like it gets pulled into this, when this bond forms, this excess energy is basically, exerted as it tries to escape. And as it tries to escape, this energy is spent until a point where, any excess energy is used up and it falls into this equilibrium point where it's now just locked at this balance, right? And so this is why when bonds form, they, typically will, like a bond forms, and typically they give off energy if they form, spontaneously, or they take in energy in order to, reach a balance point, right? Or, the reaction needs to take in energy in order to break out of its current bonds and create new ones. It needs to take energy in, right? And so this is because in order to break the bond, right, you need to give the two things orbiting enough energy to have escape, it's like enough energy to achieve their escape energy. And I kind of was thinking about this, and I was like, okay, escape energy and stuff. And I was, this was another one where I was like, how do I even, go about asking about this? So it was a thing I was, discussing on, with ChatGPT. And basically, I was like, well, how much energy would it take to I was trying to relate it to, planets and stars and stuff. So I was like, well, how much energy does it take to remove the equilibrium that we have with the Earth and the Sun? How much energy would it take to, basically break the Earth free from the Sun, right? And in order to break the Earth free from the Sun, it costs a lot less energy than it would to break the Sun free from the Earth, right? So if you imagine the Earth staying still and you just moved the Sun away, right? It takes a lot more energy than it would to just leave the Sun still and push away the Earth. And, this basically got me thinking that, okay, well, then we do have this escape energy, and that different masses do, the speed is the same for each one, but the amount of energy needed to reach that speed is different. And the reason why is because of mass. But you can, it's a lot easier. I've discussed this before. It is a lot easier to get the energy equivalent through velocity than it is through mass, right? So an object that is more massive is harder to push. It moves at the same speed, right? But it is a lot harder to get it to move at that speed than it is to get something that's lighter to move at that speed. And so when it comes to things like escape energy, escape velocity, it is, all you have to do is put in enough energy to remove the smaller, part of the bond to break it free. And so I'm not saying I have all the answers on this. I haven't completely, proven this, but I think that bonds basically, if you were able to zoom down enough, it would look something like just orbital motion, some kind of orbital motion going on there on some level. Because I think that every interaction is basically orbital motion, because nothing actually is directly colliding. And if it is directly colliding, then it is combining into something else. It's not, hitting and then bouncing off and, going on about its day. Typically speaking, because that's just, I don't know, I just don't think that's how that works. So to me, it makes a lot more sense to have interactions having, given that there's so much empty space, interactions with an object are more likely just orbital interactions, not physically contacting interactions. And a method of proving this, I'm not totally certain about. You can point towards things like stars and, planets and things like that and say, look, they orbit, so shouldn't everything else? And people will say, what the hell are you talking about? You're talking about space when we're talking about the Earth, like just atoms. Those things aren't the same. And again, I disagree. I don't think it's logical to conclude that we can't drag that logic down to subatomic particles. But I have yet to prove it, in any meaningful way other than my word and my theories here. But basically, I think that every interaction is just orbital. Nothing is actually because we know that there's not a physical, if we know that there's not a physical connection between these two objects, to me, we know there's not an actual line being drawn from one atom to the other atom, but we know that they stay together, right? So, to me, I feel like there's got to be some kind of orbital interaction taking place on some level that is holding them in that point of attraction, right? There's got to be something there that is holding them at the points that they're held at, right? Because if not, what is happening between them? Something has to be happening between them that is holding them from moving farther or closer, right? And if they're, we know that atoms don't just sit still, right? Even in, solid materials, they move around a bit. We know that. And so, to me, I just, I think that it makes logical sense to conclude that there's something interacting between them. Maybe it's just the electrons that are flying around that are helping to hold them in place. You know, that's what the seeming, theory is. It has to do with charge, like positive and negative charge. But to me, what is positive and negative charge? Really, what is that? What is that really? When we think about it, like we use that explanation. Sure, yeah, it's positive and negative charge, but what does that really mean at the end of the day? And to me, that's really just more and less energy. Like one has less energy, so it is pulled in closer to the thing that has more energy. I don't know. I feel like there's got to be. It's definitely gravity. How much orbiting is happening, I'm still not totally certain about, because I'm thinking about how we have images of atoms, right? And how good these images are. Like it's pretty, like they're pretty high quality, but like we have no reference frame for what is high quality for an atom, right? We're like, wow, like we can actually see the little circles basically. But how realistic is that really of a representation of what an atom is? When you look at a black hole, do you actually see a black hole? The answer is no, you don't really see the black hole. So what if atoms are on a similar level? Like we're looking at them and we're like, wow, these spheres, how pretty, but that's not really what an atom is. We just can't quite see. We can't quite see what an atom is. So quantum tunneling seems to be more of a test of if there is a larger gravitational pull or not. This is sort of the same as saying sufficient energy or not. If there is nothing to pull it away, then it stays where it is. The larger the distance, the less likely something can grab it and pull it over to the other side. Higher energy, less mass, on average, easier to pull away. When photons quantum tunnel through a glass cup or anything, they continue all the way through, because once they are in the material, there is no direction more favorable than their current trajectory, and so they move through the lower energy field till they escape. It could be possible that lightning or electrical arcs are the quantum tunneling phenomenon on a larger scale. Not totally sure. Energy or mass is able to jump across a seemingly impossible gap, right? So in quantum tunneling, there's not like a physical wall or hole that these particles are in, right? But there's an energy gap. And so they shouldn't have enough energy to be able to jump out. But on occasions, they can and do. And I think, if my theories and what I've been talking about, it tracks that this quantum tunneling that we see is really just particles, by chance, having an interaction where, there's not enough energy to jump that gap inside the particle. However, when a larger particle moves by, right, there's energy gap here. It shouldn't be able to jump out, right? It doesn't have enough energy to jump out. But by this particle moving by, basically it lowers that energy gap down to a point where now it does have enough energy to be pulled into, into this other side of the gap. And now it's on the other side, because by another particle of larger mass coming by, it has reduced that gap. And I think that makes sense. I think that is a logical way to kind of look at it, and rather than it being this random chance that, oh, it might just boop, 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 there it goes. Oh, it hopped over. It's more of a, it is a random chance, but it's not because, it just felt like hopping over. It's because there's a random chance that a particle will be there and lower that level. And when a particle is there, it lowers the level and it flies across. And then boom, you have the tunnel formed. But it's not necessarily the particle that's doing the tunneling. It's more that the other particle that, we're not necessarily observing or focusing on is allowing for it to jump across. And so, pretty much that's the general gist of it. And so I bring up lightning here because, you have clouds way up in the sky that will strike the ground, and energy is able to jump from the clouds to the ground. There's this seeming energy gap, right? There's this seeming gap, and the energy shouldn't be able to jump that distance, right? It shouldn't be able to go from the clouds to the ground. But if a certain charge builds up on each side, it can, right? Each individual particle does not have enough energy to make that jump, but collectively, they do, right? And so I feel like something along those lines could also be what's causing this quantum tunneling, at the fundamental level. Maybe it's a charge buildup at a level that we don't see. So it looks like, oh, there's not enough energy there, but like when you build up a static charge, there's an energy differential. And it's not that one side has tons of energy necessarily, but it's that there's a significant gap in energy between these 2 points that, this, like, the energy needed to jump is reduced because of just the strength of, I guess, attraction, right? And I know that it's not a one-to-one what I was saying before, but I think that at least one of those options is probably more likely than a random happenstance jump, right? And if you really think about it, like how often lightning strikes, like there's a lot of lightning during a storm, but it's not constantly happening and it's not constantly striking like every point. It's a rare occurrence, right? So it does track with the unlikeliness of a quantum tunneling event to take place, right? But there's also cases where some storms have a lot of lightning, whereas other storms have less, right? So there's situations where you could have quantum tunneling happening because the circumstances are, really high. And we know that when you're, like, we've gotten to a point with transistors that you now have to worry about quantum tunneling because when you make them too small, you get quantum tunneling happening more often, right? And I think the reason for that is because, when you have a tinier gap, you allow for it to, you make it easier for a particle to interact with, come close enough to lower the level of energy needed for it to jump across. And so, I don't know if I could really flesh that out much more than I already have, right? I think that basically quantum tunneling is not this randomness, weird quantum thing that we can't understand. It just kind of happens. I think that it is entirely understandable, entirely, explainable, and it comes back to gravity again, because everything can, I think, be tied back to gravity. You just got to go to small enough levels of it, and you can't just say, oh, well, it no longer is relevant at the small level. And so Yeah, I don't know. I think it's so funny when people say that gravity is so weak. And because if I'm right, like that's just going to be such an iconic quote. Gravity is so weak. It has no effect on the strong, like the strong force is so much stronger than gravity. Meanwhile, it was gravity all along. I don't know. I just think that'll be so funny. Anyway, peace out.